Hi, welcome to the next section, combining different algorithms into an ensemble. At various points, we pointed out every algorithm has its own strengths and weaknesses, and we took note of how to spot and overcome these weaknesses. However, wouldn't it be great if we could simply stack together a bunch of average classifiers to form a much stronger ensemble of classifiers? In this section, we'll do just that. Now we start with the first video of this section, understanding ensemble methods. The goal of ensemble methods is to combine the predictions of several individual estimators built with a given learning algorithm in order to solve a shared problem. Typically, an ensemble consists of two major components: a set of models, a set of decision rules that govern how the results of these models are combined into a single output. A consequence of this procedure is we get a multitude of opinions about any given problem. So, how do we know which classifier is right? This is why we need a decision rule. Perhaps we consider everybody's opinion of equal importance, or perhaps we would want to weight somebody's opinion based on their expert status. Depending on the nature of our decision rule, ensemble methods can be categorized as follows: averaging methods, boosting methods, stacking methods. The same three categories of ensemble methods are illustrated in the following figure. Ensemble classifiers afford us the opportunity to choose the best elements of each of the proposed solutions in order to come up with a single final result. As a result, we typically get much more accurate and robust results. Averaging methods have a long history in machine learning and are commonly applied in fields such as molecular dynamics and audio signal processing. Such ensembles are typically seen as almost exact replicates of a given system. An averaging ensemble is essentially a collection of models that train on the same dataset. Their results are then aggregated in a number of ways. One common method involves creating multiple model configurations that take different parameter subsets as input. Techniques that take this approach are referred to collectively as bagging methods. Bagging methods come in many different flavors. However, they typically only differ by the way they draw random subsets of the training data. Pasting methods draw random subsets of the samples without replacement. Bagging methods draw random subsets of the samples with replacement. Random subspace methods draw random subsets of the features but train on all data samples. And random patches methods draw random subsets of both samples and features. In scikit-learn, bagging methods can be realized using the meta-estimators bagging classifier and bagging regressor. These are meta-estimators because they allow us to build an ensemble from any other base estimator. We first import the bagging classifier and k-neighbors classifier. We build an ensemble from a collection of 10 knn classifiers. The bagging classifier class provides a number of options to customize the ensemble. They are n estimators. This specifies the number of base estimators in the ensemble. Max samples. This donates the number or fraction of samples to draw from the dataset to train each base estimator. And the last one is max features. This donates the number or fraction of features to draw from the feature matrix to train each base estimator. This gives us the ultimate freedom to implement any kind of averaging ensemble. An ensemble can then be fit to data like any other estimator using the ensemble's fit method. Here we've used an n estimator. For example, if we wanted to implement bagging with 10 knn classifiers with k equal to t05, where every knn classifier is trained on 50% of the samples in the dataset, we would modify the command as shown. In order to observe a performance boost, we apply the ensemble to some dataset, such as the breast cancer dataset. As usual, we follow the best practice of splitting the data into training and test sets. Then we train the ensemble using the fit method and evaluate its generalization performance using the score method. We get the accuracy as 93.7%. The performance boost will become evident once we also train a single knn classifier on the data. Without changing the underlying algorithm, we were able to improve our test score from 91.6% to 93.7% by simply letting 10 knn classifiers do the job instead of a single one. You're welcome to experiment with other bagging ensembles. Similarly, we use the bagging regressor class to form an ensemble of regressors. For example, we build an ensemble of decision trees to predict the housing prices from the Boston dataset. The syntax is almost identical to setting up a bagging classifier. Of course, we need to load and split the dataset like we did for the breast cancer dataset. Then we fit the bagging regressor on XTrain and score it on XTest. As in the last example, you'll find a performance boost accuracy for a single decision tree. Of course, we wouldn't just stop here. Nobody said the ensemble needs to consist of 10 individual estimators, so we're free to explore different sized ensembles. Another approach to building ensembles is through boosting. Boosting models use multiple individual learners in sequence to iteratively boost the performance of the ensemble. Typically, the learners used in boosting are relatively simple. A good example is a decision tree with only a single node, a decision stump. We want the individuals to be weak learners, so that we get a superior performance only when we consider a large number of individuals. At each iteration of the procedure, the training set is adjusted so that the next classifier is applied to the data points that the preceding classifier got wrong. Over multiple iterations, the ensemble is extended with a new tree at each iteration. For example, we'll build a boosting classifier from a collection of 10 decision trees as follows. These classifiers support both binary and multi-class classification. Similar to the bagging classifier class, the gradient boosting classifier class provides a number of options to customize the ensemble. They are N estimators. This denotes the number of base estimators in the ensemble. Loss. This denotes the loss function, to be optimized. Learning rate. This denotes the fraction by which to shrink the contribution of each tree. Max depth. This denotes the maximum depth of the individual trees in the ensemble. Criterion. This denotes the function to measure the quality of a node split. Min sample split. This denotes the number of samples required to split an internal node. Max leaf nodes. This denotes the maximum number of leaf nodes allowed in each individual tree, and so on. We use N estimators in our code. We can apply the boosted classifier to the preceding breast cancer dataset to get an idea of how this ensemble compares to a bagged classifier. But first, we reload the dataset. Then we find the boosted classifier accuracy on the test set. It's a little under 1% better than the preceding bagged classifier. We would expect an even better score if we increased the number of base estimators from 10 to 100. In addition, we might want to play around with the learning rate and the depths of the trees. Implementing a boosted regressor allows the same syntax as the boosted classifier. We've seen earlier that a single decision tree can achieve 79.3% accuracy on the Boston dataset. A bagged decision tree classifier made of 10 individual regression trees achieved 82.7% accuracy. But how does a boosted regressor compare? Let's reload the Boston dataset and then split it into training and test sets. We want to make sure we use the same value for random state, so that we end up training and testing on the same subsets of the data. Then we find the boosted classifier accuracy on the test set. As it turns out, the boosted decision tree ensemble actually performs worse than the previous code. This result might be confusing at first. After all, we use 10 times more classifiers than we did for a single decision tree. Why would our numbers get worse? You can see, this is a good example of an expert classifier being smarter than a group of weak learners. One possible solution is to make the ensemble larger. In fact, it is customary to use on the order of 100 weak learners in a boosted ensemble. Then, we retrain the ensemble on the Boston dataset. We get a test score of 89.8%. What happens when you increase the number to 500? There's a lot more we could do by playing with the optional parameters. As you can see, boosting is a powerful procedure that allows you to get massive performance improvements by combining a large number of relatively simple learners. All the ensemble methods we've seen so far share a common design philosophy: to fit multiple individual classifiers to the data and incorporate their predictions with the help of some simple decision rule into a final prediction. Stacking ensembles, on the other hand, build ensembles with hierarchies. Here, individual learners are organized into multiple layers, where the output of one layer of learners is used as training data for a model at the next layer. This way, it's possible to successfully blend hundreds of different models. However, these models can be very powerful, as seen, for example, in the Netflix prize competition. The most successful models in the competition used to indicate stacking ensembles that not just combined different layers, but extracted from each layer the parameters that were the most effective, and used them as meta features for training the next layer.